Yet another calculus integral. Determine if this integral exists, and if it exists, determine its value. And we have two totally valid options here. One, to find out whether this integral exists, you could literally try to compute it. You're either going to get a number and then you're going to be like, well, I guess the integral existed. Or you're going to get dne does not exist, and then you'll say, well, I guess this integral diverges. So that's one totally valid technique. You could also use a test. Now in Chapter 11, in Sequences and Series, we're going to have more fancy tests that we can use. For now, we just have the comparison test. There's a drawback to this, though. If the test tells you that the integral converges, the test won't tell you what the answer is, and then you have to go back and do more work to figure out what the integral is actually equal to, which is super irritating. But if the integral diverges, the test is usually going to be faster. So it's kind of like a gamble, right? You got to pick your poison. So I'm actually going to do this both ways for you. To try to just find the integral and see what it's equal to, I'm going to do a substitution here. I have u equals x squared minus 4, so that du equals 2x dx. And then my antiderivative is going to be equal to, well, not my antiderivative, my integral is going to transform to 1/2 times the integral of 1 over the cube root of u. And just a note on where that's coming from. I took the x times dx and I replaced it with 1/2 du using this. And I took the x squared minus 4 on the bottom and I just replaced it with a u. That's how I did that. So this guy, total joke, use the power rule. So that's actually going to be equal to 1/2 times 3/2 u to the 2/3 power plus c. And I do a little back substitution and bam, antiderivative. Okay, I got my antiderivative. Let's go back to the main problem. Here is my improper integral. Here is that improper integral expressed properly as a limit as t goes to infinity. And notice the infinity symbol replaced with a t right there. So nice. Next, I replace the integral here with this evaluation here. This is the antiderivative, and then I have it evaluated from 3 to t. Next, I need to actually do the evaluation. So notice how this limit is still written here. If you don't have the lim still, it isn't right. So here is the expression with t substituted, and here is the expression with 3 substituted. Okay, so this limit does not exist. Can you tell? We have here the limit as this expression, as t goes to infinity of this expression. T is getting huge, which means that t squared minus 4 gets huge, which means that t squared minus 4 to the 2/3 power gets, not quite as huge, but huge, okay? So this limit is like infinity, and the whole thing just doesn't exist. And in our new vocab, you say, oh, this integral diverges. So there's your answer. Okay, so could we have done a test? Could we have done the comparison test to find that answer? Absolutely, and here is how it works. If I can think of an f, some function, where that f is lower, less than or equal to my integrand at all times, and if this improper integral of the smaller f function, if that integral diverges, then the original integral diverges, okay? So I just need to think of a function that's smaller than my integrand and is easier. And that function is going to be cube root of x. Why? Because cube root of x is literally equal to x over the cube root of x squared, right? It's x to the 1 divided by x to the 2/3. That's how that works. And then that function is less than or equal to x over the cube root of x squared minus 4, right? Can you see how the only difference there is the minus 4? Also, this easier integral, this integral of f from 3 to infinity, that integral diverges because the power, that 1/3, is greater than -1. That's a theorem from the lesson that you can just use. You can say, oh, well, the power is 1/3, divergent. So you have all the conditions met of your comparison test. You thought of a function that was smaller, and that function, that integral of that function was divergent, so you just say, boom, integral diverges, problem solved. But like I said, you either luck out and the integral is divergent and you don't have to do hardly any work, or the test is non-conclusive and you got to go back and try to find it anyway, which can be irritating. But hey, it's calculus.